All right, so we're going to look a little bit more in what are called one-dimensional collisions and look at collisions between objects. If we have a system where no net external force acts on a system, what we call an isolated system, basically all the external forces cancel each other out, then momentum is conserved in those collisions. That P initial equals P final for the system. Now, in some collisions, but not all collisions, kinetic energy is also conserved. These are actually a special type of collisions that we'll look at later on in this lesson. However, in a large number of collisions, kinetic energy is lost somewhere, either converted to heat and friction, or one object gets damaged and so some of the energy goes into damaging the other object. Sometimes there's some energy lost to thermal energy in that collision, energy lost to sound in that collision, all sorts of other places where energy could get lost in collisions. So we actually have a term for collisions where energy or where both kinetic energy and momentum are conserved. These are what are called elastic collisions. This is different than inelastic collisions where momentum is conserved but kinetic energy is not conserved. Generally speaking, kinetic energy is lost. Now we have a third type of collision, what we call completely inelastic. These are collisions where objects collide and are stuck together. In sample problem 2 that we did in the previous lesson, that would be an example of a completely inelastic collision. The objects are stuck together after the collision. Kinetic energy is not conserved in those collisions. So let's look at an example where a collision is elastic. So two balls are rolling across a table and collide with one another in an elastic collision. One thing to kind of watch out for, at least with the English language, an elastic collision and an elastic collision and inelastic collision, you have to really be careful when you're saying those two terms. Usually I would say, if I was to actually say this out loud, I'd say collide with one another in a collision that is elastic to avoid that confusion. We have ball 1 with a mass moving to the right with a certain velocity and ball 2 with a mass and moving to the left with a certain velocity. And it wants me to determine the velocity of both balls after the collision. Now this is a little bit more complicated because I only know 4 pieces of information and I really have 2 unknown pieces of information. I can't use conservation of momentum alone to solve that problem, but because this collision is elastic, I know that kinetic energy of the system is conserved as well. If I had the kinetic energy of both balls before the collision, it has to be equal to the kinetic energy of both balls after the collision. So what I now have is 2 equations with 2 unknowns that I could solve. So I'm not going to go through the algebra. If you are really interested in working through the algebra, ask me about it. We can solve it out. It's a process that takes, I don't know, a good probably 15 minutes to algebraically solve this. There are a few tricks working through this that make your life a little bit easier as you try to solve this one out. But we have 2 unknowns, 2 equations. It is possible to solve those 2 equations for those 2 unknowns. And here are the 2 solutions you end up with. What you notice about those solutions is they look fairly similar to one another. V final 1 is equal to V initial 1 m1 minus m2 plus 2m2 V initial 2 over the sum of the masses. And V final 2 equals V initial 2 times m2 minus m1 plus 2 times m1 V initial 1 over the sum of the masses. I believe your textbook also takes this problem from these relationships and gets to these 2 equations. You can also look that up online. There are several other places where they do that derivation. Now the advantage to having these 2 equations is I can now just plug my numbers in and go. What I find is the velocity of ball 1 is negative 1.83 meters per second, which means it's now moving to the left, and the velocity of ball 2 is to the right at 0.67 meters per second. So a good example of a collision which is completely inelastic is what we call a ballistic pendulum. And a ballistic pendulum I have here shown to the right. It's one way that's used to measure the speed of a projectile. If I wanted to figure out how fast is the speeding bullet, this is one way I could do that. So the ballistic pendulum consists of a block of wood with a mass of 2.5 kilograms and is suspended by a thin string. And a 0.01 kilogram bullet is fired into the block, and the block with the bullet swings to a height of 0.65 meters from its original position. Determine the speed of the bullet. Wow, That's kind of an interesting problem. So here are the things that we know. We know that the initial velocity, at least of the mass, is 0, or of the block is 0. It's just sitting there initially. We know the mass of the two objects. I know I'm saying the initial height is 0, and the final height is 0.65 meters. So the two things that I don't really know, I don't know the initial velocity of the bullet, which I really want to know, but I also don't know the final velocity of the mass, or the block, and the bullet right after the bullet sticks into the block. So one relationship I have is that I know that momentum is going to be conserved in the collision. I know this is a completely inelastic collision, so I know this equation is going to be true. But I also can use conservation of energy in this problem. The reason why I can use conservation of energy is after the collision, the kinetic energy of the block and the bullet, as the block starts to swing up, is going to get converted to potential energy of the block and the bullet. So I could say, well, 1/2 m1 v2 m2, and I'm calling this v final because it's really the final velocity of the collision, but it's really the initial velocity of the swing, is equal to m1 plus m2 gh final. So this gives me a way to solve for how fast are the block and the bullet moving before they start to swing up. What I could then do is plug that v in here and then work backwards to find the initial velocity of the bullet. So if you solve some things out, first of all, the mass of the system cancels out. I get 1/2 v final squared equals gh final. I can solve for v final squared, square root of 2 gh final. And there we go. I could plug that in right here. I know the initial velocity of the block is 0. And then I could divide by m1 to find v initial 1. If I plug in all the numbers that I knew from the previous problem, I get 896 meters per second is the velocity of the speeding bullet. This is one way that you can use to find the speeding bullet. The ballistic pendulum is a neat problem because it deals with conservation of energy after the collision and then conservation of momentum during the collision. It's what I would consider to be one of those big idea type problems that uses multiple concepts to solve that problem. So the next lesson we'll start to look at collisions in 2 dimensions and see how do we deal with collisions that happen in more than one dimension or direction.